didn't turn it. So now I have to turn it in.
All right. It's not the worst problem to have.
I know. I also forgot about the footage.
So we're on this. For the past two labs. It's. So. Yeah, so.
So, how's it going?
It's going.
It sure is.
Yeah.
Quiet character. Wasn't it?
Yeah,
No.
I mean, I'm here.
Okay,
That's,
thank you.
at least I made it here,
You made it.
right?
It's progress.
I mean, I haven't even looked at the homework
Okay.
because I've been doing the midterm.
Is it too much?
Do we have a homework?
It's been a struggle for me personally.
Is it too much? I mean, I can extend the deadline.
I mean, maybe.
I don't need to know if more time is helpful.
Maybe, I mean, ultimately, it's just been, I mean, for a lot of my stuff, I mean, for his stuff too, a lot of our classes have sort of just retrograded and everything's just hitting at the same time.
Crunch time.
Yeah, but I don't know. I mean,
Like
it's
you're
just,
getting crunched.
yeah, yeah, a little bit. I don't know. I mean,
Well, I'm flexible, guys. I mean, I haven't been, I mean, this is not like the Calc 3 course where I've got hundreds of students and have to keep everyone on the same page. If we got to slow down, we got to slow down. That's okay. Just let me know. And, you know, if everyone's feeling a little overwhelmed, we can slow it down and I can extend the
I
time
mean,
a
maybe
little
just
bit. And
a couple more days for the homework.
why don't I do that? I'll push it to Wednesday.
That's,
And then, and you know, I'll try to slow the lectures down a little bit and maybe rework the schedules just to make sure people are following. I don't want people to get lost. We don't have, we can just
Just
talk.
this week with the midterm. It's
Yeah,
just the
that's-
constant
yeah.
looming of having a
Yeah.
giant midterm.
because, you know, I personally, they said prioritizing that.
Yeah, you should prioritize that.
Yeah.
But, okay. All right, well, I'll do that. I'll put it, I'll send an announcement later today. But, you know, we can still talk about things. You guys can tell me what you want. Look at. I mean, whatever. I mean, if you have a question about the midterm, that's fine too. I can just, I'm not gonna like solve it.
Yeah.
But I can like explain things too.
Problem 5 has probably shaved 10 years off my life.
Yeah.
Now?
Just 10.
Yeah, just 10.
Which was 5? Which one was 5?
There was the one about the discrete isometries of the plane, then H is the group translations. If the stabilizer A equals that an H is that a G, what are the possible values of G?
Of the index. Yeah. Cool.
Yeah, that's where I'm at too.
I mean, maybe a thing to think about there is like, you know, you've got this, you got some discrete thing. And what it's saying is it's saying that if you fix like this red point, this group is gonna, subgroup H is gonna do everything that the group G does that fixes that red point. The subgroup H looks exactly like, you know, does all the rotations, reflections, etc. around that red point. And then it has all the translations. So it takes the red point and it will translate it to every other, translate that G does. H. So H, you should be thinking H looks a lot like G. So the question is really, I mean, a way of rephrasing that question is H G? And if not, how different can it be? If it has all of that, what might it be missing? And think on that.
A book chapter.
Or at
Chapter
least-
6, what was the one with
I guess maybe like a micro 5-minute crash course on a little more about stabilizers.
I mean, to some extent, I'll say this question is sort of inspired by Arton's discussion in the beginning of the section on crystallographic groups. If you look at that section and just read, which is not, it's not, he doesn't prove theorems there. He just talks about kind of some subtlety groups. And that's where that question kind of came, a reaction to that. Guys. What else? I mean, we can look at some homework stuff. I mean, even though I give you more time, you know, still might be good to have. things to look at. Let me pull it up. I can also, you guys tell me what it is. I can, we can look at a couple of them. I thought you guys came after every lecture, you went and did homework on that lecture right away. Isn't that the way you guys do things?
On
That's a bit
occasion.
optimistic.
I'm sure. which
I'm an
one-
optimistic guy. I believe the best of you guys.
First week that happened.
Yeah,
That was yeah, that was our honeymoon
and
period.
everything.
When we were still finding the determinant.
Right, exactly. I lured you guys in, didn't I? That's right. And here's a matrix. And what do you? Right. Yeah. Now let's talk about rings and fields right now.
All downhill from there.
It's interesting.
It is interesting. All right, guys, tell me what did I sign? I don't remember.
It's from chapter 11. There's stuff in sections 1, 2, 3, and 4.
Can you tell me the problems?
Yeah, so in chapter 1, there is 3 and 9.
Section 1,
Yes.
3 and 9.
Sorry.
Okay.
And then in chapter 2, there's just problem, or section 2, there's just problem 2.
Okay.
Section 3 is problems 2, 9, and 12. And then it's section 4 problem.
That's right. Well, let's take a look. Should you look at one of them?
I'm just
Tim,
trying
do
to
you have
look at
anything
one
you wanna
which
look at?
I'm just trying to find the one I see would be most confusing.
Section 4? 4.4?
Yep.
Okay. Okay, so are these rings isomorphic? Are these rings isomorphic? I gotta be honest. I got it. So what do you guys think?
Don't they send it, they'll both send it to C.
Oh, you're, I see. Yeah, that's an interesting idea. Okay, so Gail, you're suggesting take these rings and embed them in C. Map them to C. Yeah, there are homomorphisms between them. You can take this and go C, setting X, I times the square root of 7. Okay. We did the same thing with the other. See what image we got. This will go to root of 7 halves, it looks like. Sure. So how are we going to, what are we going to, oops. How are we going to go from here? So that's we have two subrings of the complex numbers.
Set the x's to each other so that they're continuing each other because
Set the x's. So I see. So, well, okay. So you would want to find an isomorphism, right? If they were isomorphic. So you'd want an isomorphism. So what would you need to have an isomorphism? Okay. Right, and surjective. Words 1-to-1 and on-to as well.
it needs to exist. Projectivity. I root 7. I root 7. What we can't do.
Right. I mean, I don't know the answer, so I'm trying to think of the answer here. It's not. It's not really clear here. I suspect, but my first instinct is that this is not, that they're not isomorphic, but you know, you never know. Some things are tricky. So I don't know. I have to think about it, to be honest. I guess. Okay, so here's an idea. Yeah, I see. So let's see here. No. Yes.
So
What we're talking about is
I can't hear you.
oh, sorry,
Speak up.
Arden made like the image, so he sent it this morning.
Oh, the killing things?
Killing thing.
Yeah,
So on like the right-hand side of this mapping.
are you talking about this problem or is
Yeah,
your
it's
side?
this problem.
Uh-huh.
On the right-hand side of this supposed isomorphism,
Mm-hmm.
aren't all multiples of, well, actually,
It's not isomorphism. These are just homomorphisms.
no,
These are not isomorphisms at all. These are homomorphisms. So, yeah, go ahead.
sorry, if you eliminate anything that is x squared times 2, aren't you effectively eliminating a possible value that's not possible less? Or no, you may be missing that.
X squared times 2. What I'm just saying, if you send x, there is a homomorphism from, all I'm saying here is I'm saying there's a homomorphism from here to here, from here to here, which sends x to I times the square root of 7 to 2. That's all I'm saying. The image of it is z to, it will look like this. It will look like a plus b times I square root of 7/2, where a and b are integers. So that's what the image looks like, which is not quite easy to see what it looks like. It's pretty kind of messy. It's not that bad. It's kind of like it's a lattice of sorts. So it'll be like, actually, it's more like a rectangular lattice. But the problem is you can't really see from the rectangular lattice whether or not there's an isomorphism here. However, I'm starting to think now I can understand what's going on here. Yeah. So I think this is false. And here's the reason why. Well, okay. So I went through a few different ways of trying to think about this. But here's what I've come to. Let's suppose you have an isomorphism like this. Okay, then it has to be an isomorphism. So all the structure on one side has to be the same as the structure on the other. Now, you don't necessarily, so what's hard about this is like you don't really know where x goes here. X could go, it could go to some mysterious element that you're not aware of what's going on. However, you do know where 1 goes, right? 1 goes to 1. It's a ring isomorphism. But if 1 goes to 1, then 2 goes to 2. Because 1 plus 1 is 2. Right? Yeah, good. But now that means that the principal ideal generated by 2 goes to this principal ideal generated by 2. So in other words, that means that there is this ideal 2 inside of both of these rings. And this isomorphism has to send that ideal to that ideal, no matter what. Like all the multiples of 2 have to go to all the multiples of 2, because 2 goes to 2. That's isomorphism. Well, 2 goes to 2, and it's an isomorphism. so like 2 is equal to 2 times any element R. Like this is a commutative ring. So it's like all elements times 2, where R is an element. Let's call this ring R and this ring R prime, so I don't have to write it over and over. Where R is all of the elements. Now take phi and see what happens. So then you get phi of R times, and I said 2 goes to 2, so this is times 2. This goes to this set, R and R. Now, as I said, phi is an isomorphism, is bijective. So the set, as we range over all R here, this ranges over all R prime. So this is equal to R tilde R, which is 2. So these ideals are, of course, they correspond to each other under this isomorphism. No matter what the isomorphism is, it has to do that. But now quotient both sides by it. So if there's an isomorphism like that and it sends one ideal to the other, then the quotients will also have to be isomorphic. So that means that if I go z over x squared plus 2, the ideal generated by these two, this should be isomorphic to this. 2x squared 7. Now you apply this, actually what you were talking about, this kill rectangle. Awful. But okay. Guess hunters might like it. Okay. So instead of quotienting by this first and then this, quotient the other way around. Quotient by this and then this. You quotient by this first, you get f2. Z mod 2 is f2. And you're quotienting by this x squared plus 7. You do that over here. Well, here if I quotient by this, I'll get f2. I get the same kind of thing. I get f2x. But now I'm quotienting by 2x squared plus 7. But 2 times x squared is 0 in f2. Right? 2 is 0. So then this is mod 7. 7 is invertible mod 2. So this is actually 1. In other words, it's the whole ring. This is 0, the 0 ring. However, this is not 0. This is not a 0 ring. You're quotienting out by a polynomial. So, no isomorphism.
How are we able to turn that 2x plus 7? Like I understand, like it goes, so how do we know that x goes to 0 when it's being quotiented by that, I guess?
Well, I don't know that x goes to, well, what do you mean? So,
Because you had 7, you have that when you quotient by 2, it's it's the polynomial x. over
X doesn't-
7.
okay,
Like, because you have the 2x squared plus 7 in the denominator.
yeah, this thing,
Yeah, and then you turn it into a 7.
it's 7. Well, 2 is 0.
2 is 0?
Once you're in here, 2 is 0.
But how did you take the mod of the what you're quotienting?
I think the mod.
I think that's, I'm just confused how like.
Right, so this is this kill rectangle. So the point is this. Deadly rectangle. Quotient, there's sort of a commutativity of quotienting. And quotient by both. By quotient by the ideal generated by both of these things, then Jesus kill. Right, and then something like this. For 19. That's the worst, I tell you. Okay, so kill 2. Kill. So this is this rectangle that he has in there, which is, this works fine. If you have an ideal generated by 2 elements, you can kind of quotient out by 1 and then the other. It doesn't matter which order you do it in. So I'm saying, okay, this is very confusing. It's a confusing polynomial to me. I don't know what's going on. But if I kill 2 first, well, I've killed 2, so now this is 0. It's 0 times something. So that's 0.
Okay. That makes sense.
That's where 7 is 1. Yeah, tricky stuff. Fun stuff.
The magic that you use to determine that quantity or
I just saw the coefficient 2. I said, boy, I wish that would go away. And so I made it go away.
If I do that with the exam problem, I wish it would go away.
It's gone. You can. I mean, I'm not saying what will happen. You're free, man.
Problem 1 cancels with problem 5, so they're just tangent. So they don't add anything.
Some kind of like data. This thing sort of midterm response. All right, so that's that one. Any other ones? Should we look at something else? Okay. I think 3.12 should be pretty straightforward. I'll never bring this up. That's actually a good one. Huh?
I'd be okay with
3.9?
Yeah.
You'd be okay doing 3.9, or you okay? Or you want us?
Yeah, yeah.
Like, yes, I guess. All right. Hey. So nilpotence is a very, very studied topic in algebra. A lot of cool rings are and groups. There's notion for nilpotent groups. And anyway, a lot to do with derivatives, actually, in some sense, differentials. But anyway, so X nilpotent means nilpotent just means that I can find some power that's zero. Not a very familiar kind of thing in just ordinary calculus or something. Of course, you would conclude X zero if you saw this outside algebra. But you know, you can think of a ring like example Rx, you quotient by the principal ideal generated by X to the n. Right? That certain X in this ring, X to the n is zero. It's a quotient killing this sort of power. But X is non-zero. So you get things like that. I won't bother you with the beauty of the dual numbers, but like, this is an alternative way of doing calculus, a completely alternative way of algebraic, but relying on the thing. Okay, so we want to say that 1 plus, if this is true, 1 plus X is a unit. You know this, the answer to this, so why is it true? So you need to find a multiplicative inverse of 1 plus X. Any thoughts? What? What is that? What is that? What do you mean 1 over? What is 1 over?
To the -1.
Oh, what does that mean? I'm just picking.
It's okay.
What does it mean? So, I mean, the thing is, what can we do and what can't we do, right? In the integers, you can't do that. Like I say, X is a number, like X is 3. You can't go 1 plus 3. And that, there's no 1/4. Doesn't exist in the integers. So, you know, if you have an inverse, then everything's a unit. If you're in a field, everything's a unit. So that's what it's asking. Is what is it? No doing that. I'm saying that it's a unit because I can take its inverse. But this is good. I actually kind of like this. You're close here. Kind of. By which I mean, if you went to your friend, if you have friends, and overrated, L2, Ask them about this. What would they say? It would say something about a sum. Exactly. Big old sum. Big series. Series. I can't do it. Right? What's the series? What would they write? They would say if x has an absolute value less than 1, did you know this is the same thing as
X to the n over n factorial. No, that's either.
on either the x? This is more like a geometric series.
X to the n. Some over n or some over n.
Close, but that would be this.
Over n.
Close. You have takers?
I cannot remember.
Nobody remembers.
My
that.
serious education happened during COVID.
Oh, don't use that excuse on me. I get that from my Calc 3 students. They're the worst. They're great. Of course. They're not the worst people, but they say things like, I can't remember anything because I was in COVID. What am I supposed to do?
Can't remember things.
I tutor Calc 2, so I should know. But I don't.
They're good. You guys are brilliant people. Come on.
But it's one,
You're the future of the world and stuff.
1 minus x plus
Hey.
squared, right?
Plus x squared. Right?
Yeah, there's negative 1 of them.
Yeah. And this is 1 minus negative x. So the series you were talking about, this geometric series. So if you wanted to write this in a ring, you could write this, but there's only one problem in a ring. You can't, there are no series in ring. Well, there are actually, but not, that's a different story. Okay, like, there's no, this doesn't exist in ring. However, what do we have to come to the rescue?
Actually, n is 0.
It's no potent.
But any power of x is 0?
Well, any power after x to the n is 0 times some other thing. So this is all 0.
But do we know what n is?
Oh, you need to? And it's a natural number. It's not like square root or anything. I mean, it's not like, it's a positive natural number. Positive integer. Like, for example, if we know that x cubed equals 0, right? And I go, and I look at this, I multiply this times 1 plus x. Well, I get that, 1 minus x plus x squared. I get x times that, x minus x squared plus x cubed, right? Well, I get cancellation here, and then x cubed equals 0. So I get 1. That's the inverse. If x cubed is 0. X, and if it's n, then you just do, I mean, here it's negative 1. Calc 2 is useful for something.
It's interesting.
Modern algebra. Calc 2 is really the worst of all the calcs. I really believe it. I mean, it's really great if you could spend like a year or two on it in a different way, completely different way, but otherwise, people like it. Myself.
Felix is just a bunch of Taylor series.
Well, no, I love it. I mean, Taylor series and approximations, that's great. That's fine. It's more that like techniques of integrating. First of all, when you do series and sequences in Calc 2, it's super rushed. And you don't have time to really like understand what's going on. And then there's the whole part of Calc 2 where it says techniques of integration, which is just like getting your teeth drilled out for like 5 hours a day or something. Just awful. I mean, it would be fun to play with it, but that's sort of like something you should do. So, Oh, P. Suppose that R has prime characteristic, which means that P times 1 is equal to 0. So like 1 plus 1 that. Prove that if A is nilpotent, then 1 plus A is unipotent. Wow. Unipotent. Some power of 1 plus A is equal to 1. So it's not just invertible. This to some power is equal to 1. Better guess what power. E. Not alone is not really prime. You guys ever notice, you guys ever done Pascal's triangle? You know Pascal's triangle. Everyone knows Pascal's triangle. You ever noticed anything about it?
A lot of things.
There's a lot of things about it. I guess, I don't know, do I need? It's N. Sorry, A is, okay, so yes, we have to probably do something like P, well, it's probably, is it sufficient?
Coefficients.
I think I need a power of P. Something like that. I think P to some power that's greater than that. I don't know. What am I talking about? P should be fine. What am I talking about? What did he say here? I don't even know what he said. No, you're right. Not you, me. I'm right. I need some power of P. I'm really tired right now. It's been a long, very long week. So this is, yeah, I want P. I don't really need N, but I want some power of P that's greater than N. So it doesn't really matter. I can say P to the R, but I want P to the R to be greater than N, where A to the N equals 0. That's what I want. Did you ever notice anything about Pascal's triangle? Let's. I'm going to show you some.
Like, what's
Yeah.
specific?
Huh? What? Did you say something? What is that?
That if you move along the diagonal from top to bottom, that's horrible.
Yeah. Well, you've got the binomial coefficients along the diagonals. That's true. They're very important. Very important feature. A lovely triangle.
There's something you do with blocks.
Yeah, random walks. You find something. I'll show you something else too. Have you ever seen the colorings of the Pascal triangle? You guys ever seen that? You go to like math circles or something. For kids, like elementary school kids, we do this. I used to get back when math circles existed. Because they will again. I'm just going to go up this power. Maybe I should do one more. Should I? Not really. Can't even count. So. Okay. I should do like a few more. What is this? 36? You guys have to help me. 70 plus 14, 84. Is that right? No, that's wrong. Is it right?
Yeah, that's 84.
Did I screw up?
Yeah, no, it's 84. 84, then 126, then 84.
Oh, 84 is okay. Yeah, 126. Okay, thank you.
Then 126.
Yeah. I thought he.
Can you ask?
I'm kidding. All right. Now, look at this. Here's what I want to show you. So this is like this. This is the 0th row. First, second, third, fourth. So if I go down on the power of 2, so there's this beautiful thing you can do. You can do like you can take Pascal's triangle and you go like look at it in F2. Ever done that? Try it. I bet we can find it online. Pascal's triangle on 2. That's what it looks like. Like the ones are like black lines and like, yeah. It's really cool. These are like other pictures. Like you can look at these are other pictures. So the wise one. But they're like pictures mod other numbers. Right? You can do all kinds of things. Okay, so if you do that, but what you'll notice about it, the reason you get kind of some of those pictures is in the powers of 2. Look, if I go, okay. If I go to the powers of 2, right? I get a 0. Next power of 2 is 8. You see all of these are even. Okay. Now if you do the same thing, but you do powers of 3, and you go mod 3, guess what happens? Powers of 3 divisible by 3. 0 is 0. 9. That's why I did 9. 0, 0. 8 plus 4 is 12. That's okay. This is 0. Everything is 0. So if you look at a power of a prime in Pascal's triangle, you look at that row, and then you mod out by that prime, that whole row is 0 except the endpoints. Pretty cool. Not hard to prove, but pretty cool. Very actually easy to prove because you have the binomial coefficients are like n choose k, and this is like something factorial, and you have a big power of p, and it's that power of p is bigger than the denominators, so you have an extra factor of p. You can prove that. Once you know that, you know the answer to this problem. Binomial theorem. Is equal to the sum, I equaling 0 to p to the r of p to the r, choose I, 1 to the I, which is 1, times a to the I. Now, if p times 1 equals 0, these are all 0 by what I just said. They're the entries in the row, except for 2. First and the last. So this is equal to 1 plus a to the p to the r. But if you assume this, then this is 0. It's equal to 1. Pretty cool. Math is awesome. Wasn't it? Okay. I don't need applause or anything. I'm here every Friday, 3:30. Yeah, no, please don't. I'm embarrassed. What's going on? What else? That's it.
I'm sure that's not it.
That was, I think that was probably, without like a little hint, that one was probably pretty hard.
Yeah.
That's kind of hard to guess. You guys know how to do 3, 2.
Probably.
I feel like it's something that could be just say zeros and be uncontradicted.
Yeah, I mean, you can also, this is easier than that. I mean, so maybe just remember conjugates. A plus bi times a squared plus b squared. If you remember that, and you know the definition of an ideal. All right, guys. No other questions? You got me for 5 more minutes. Thank you.
Yes, sir. For question number 4, and showing like, so it was the question where you gave us the role of 1 to 5. Showing that the third project.
Oh, yeah. Wait.
Inner dot product, so for the third property where it has to be a definite positive.
Positive. Yeah.
A positive definite. So for that, it is doable, just symbol, right? Like, I don't have to know what F of X is evaluate to.
Well, so maybe the only thing you have to know there is that I did it for continuous functions, I think. So you have to know that if you have a continuous function, then there's going to be an interval and it's not a zero function. And there's some open set for which it's like strictly above a certain number. Right? In other words, I will say this much because it's more analysis. I guess the one thing you would need from analysis would be to like say, okay, if I've got a continuous function on an interval a to b, and f is continuous, then there exists some subinterval, really small, I don't know, like CD, with and an epsilon, strictly positive epsilon, with f of x absolute value greater than epsilon on CD. That's from continuity. That's just saying it's a continuous function. I mean, if it's not continuous, you could have like it's zero everywhere except like here, right? And make it, and then this wouldn't be true, right? Then you take the integral of this time itself would be 0. If you could make sense out of that. But if it's continuous, you know there's some subinterval. Wow. You know there's some subinterval where either f is above some value or f is below some value. You know that, then you can answer this question. Should be hard answers.
Basically, it's like if you were to -5 to 5, if you were to go from -5 to 0, 0 to 5, I guess 0 to 5 would be positive along the line that could possibly be 0.
I don't understand anything. I think that I'm just saying that you can find some fixed. So if let's say it was this big, let's say it was positive there instead of negative, doesn't matter. When I square it, I'll get, I don't know, if it's less than 1, then it's going to be like this, right? And I don't care what's happening. I know it's non-negative out there because it's something squared. I don't care about it. Because if I integrate, I know that if I've got I've got a lower bound, right? I integrate, the area under the curve is going to be greater than 0. I'm saying?
Yeah, I guess I'm saying I guess the question I was really trying to ask was, as the area under the curve kind of over the 0 over interval, as long as like we have some interval where the area under is positive, is that enough?
I mean, you should be able to break out a calculus book and have there or in any calculus book, there'll be some result that says if one function is bigger than another function, then the integral is bigger than the integral of the other function. And then you can break intervals into subintervals, and the integral will be the sum of the integrals of the subintervals. So this will be like so you can freely use anything like that, and say, okay, hey, this is calculus 1. This is fine. You can use this, I don't care. That's fine. Or whatever you did.
You think whatever we did was right?
No, I said you can use whatever you did. I'm not gonna be like, I mean, I might ignore it, I might say it's incorrect, but you can do what you want. Okay, all right, guys. Sounds good. Good luck.
Let's say after midnight, my stress levels will drop by about like 99%.
I think you guys are gonna all do great. I believe in all of you.
Remember when you said you're a pessimist or an optimist?
I am an optimist. You're a pessimist?
Yeah, yeah.
Don't be a pessimist. It's not good for your health. You have to